has a special mathematical capability that it can train off data sets which have lots of missing values. The usual machine learning methods are mathematical formulae that need all the inputs to give an output, but we find in experimental circles that not everything has been measured. And so usually you have to just throw that information away, but what we can do is nevertheless still be able to train and get that information out of it and the data that is there and go on and exploit it. And this means that we are able to bring together all possible sources of information about the material. That we can combine different sources of experimental information that come from different groups. We can merge that with a more dense data set of first principle simulations, and alongside that we can put in analytical formulae that are just represent a complete data set. We bring all of these together into a single holistic materials design tool. And that allows us to dramatically cut the number of experiments that need to be performed in order to design a new material, and because we require fewer experiments to discover those new materials more rapidly. And today I'm going to show you a series of different examples of some materials that we have developed with this technique, that have been passed on to experimentalists who've gone on to experimentally verify them, and are now being commercialized. Now, our launch customer to do this work was Rolls-Royce, who make gas turbine engines. We've got an example of one of those here, in which the air comes in through here and then it's blown out the back to provide thrust. But right in the core here, where the fuel is being burned, then we want to extract as much energy out of that fuel as possible, which by analogy to the Carnot cycle means that we want to burn the fuel as hot as possible within the engine. So to do this, we need to design some very high-tech materials that are able to sustain the very hot conditions there at the heart of the engine. And if we zoom in a little bit closer to this area where the fuel is being burned, we've got a cutaway up there, and you can see just how intricate the design of the engine is. That they set up some very complicated fluid flow in order to get the perfect fuel-air mixture, and also to provide some boundary layers of cold air to protect the material from the gases which, as they're burning it, are actually hotter than the melting point of the materials itself. And what a big challenge here is to not only make these high temperature materials, but also make materials that can be formed into those very intricate shapes, and make the plane so it's lightweight so to make it so it can take off the ground. Now traditionally these materials have been made by a combination of casting, such as the bit up here, and rolling and sheet, as from a bit further down in the engine there. But for the next generation of engine, Rolls-Royce are interested in turning to 3D printing for metals to make these components. Now that's going to require a new generation of materials that are particularly well suited to that 3D printing process. Now the 3D printing process for metals can be done by a process called direct laser deposition. We've got an example here. Here's the component that we are printing. If you look closely, you can see some stripes on its surface as it's being printed with the print head moving in this direction. And this 3D printing process comes, then the metal is blown by, a powder of the metal is blown in these jets that you can see here onto the surface of the metal, and then a laser is passed down through the centre of this print head to melt the material locally onto the surface of the object we are printing. Now we can make these beautifully intricate shapes using this, but the thermal cycles that we are putting the material through during this process is very unusual. So we're heating the material up very locally as we are printing it, and then it is cooled down rapidly as the print head moves on. And then when we come to print a layer on top of this, then we have to go back and melt a new layer on top, during which we accidentally heat up the layer below to almost the same temperature. As this is a very unique thermal cycle, very different to those that are used in methods like casting, and so we're going to need to design some new materials that are particularly well suited to that thermal cycle. Now, in order to design these materials, we are opting to use the method of machine learning, and that's one in which we start out, which tries to develop this black box in the middle, our machine learning algorithm, in which we're going to pass the composition of the material, all the different elements we put in, and the processing conditions, which will include things like time, duration, and temperatures, about 10 variables to describe that direct laser deposition process. We want a tool that we can pass them into the black box. Then out on the right-hand side, we're going to predict several of the properties that we are going to need to get right for use in the engine. So I've got a list of just some of them here. At the top, we've got the processability. That's how suitable the material is for 3D printing to avoid the cracks that are formed as you push it through several thermal cycles. We got down here the fatigue life, and down right at the bottom we got weldability. We'll see later why we have put that in. Now, for our machine learning, we have opted to use an artificial neural network, a kind of mathematical representation of how this thought perhaps the human brain works, though other things would work well also. But one thing that our method would have in common with the human brain is it first needs to go to school, it needs to be trained and learn of some pre-existing materials knowledge. So what we do is we take a database here of some pre-existing materials that we already know the composition and properties. We flick this arrow on the right around and pass that information in to train the neural network. And then once it is trained on pre-existing materials, we can flick that right-hand arrow around, put in a new material composition and predict the material properties, and then we can go and cycle through millions and millions of possible compositions very, very quickly and find the material with the right properties for the use in 3D printing for these engines. Now that's going to work well, except for the fact that 3D printing for alloys is a new process, and for this family of materials, nickel alloys, it has only been tried on about 10 different materials in the past, 10 different compositions. And that isn't very many. We have on the left-hand side around a 30-dimensional design space. That's about 20 different elements one might put into this alloy and about 10 variables to describe the processing conditions. And 10 pieces of data is not enough to inform us about a 30-dimensional space, at which point, just by plain machine learning, it would appear we're going to become unstuck. Now this is the point at which we're going to have to be inspired and think about how the traditional material scientists would operate. In that case, they would go, this process of 3D printing for alloys of direct laser deposition is analogous to another materials processing technique, that of welding. For in direct laser deposition, we are melting the material locally with a laser beam and pushing it through several thermal cycles, whereas in welding, we could be melting the material locally in space with electricity and also pushing it through several thermal cycles. Therefore, the considerations for welding, like the thermal extractivity and the susceptibility to oxidation and the phase behaviour, are going to be similar to the considerations for direct laser deposition. And one might hope that a material that's good for welding may also be good for direct laser deposition. So at which point it's obvious that we should look up all the materials good at welding and be exploring those, but we want to get that mathematically embedded into our machine learning tools so we do it all automatically. Now the way that we're going to do that is to see the advantages is we can just plot here a graph of the processability, the ability for direct laser deposition as a function of composition, and just see here we might have 3 different experimental data points out of the 10 we have available. If on those we were to just build up our machine learning model, we would generate that light blue curve where the height of it represents maybe plus or minus 1 standard deviation of uncertainty. Then, because we don't have much data to interpolate, there's quite a lot of uncertainty. And when we start to explore a new chemical space, as surely we're going to have to design new materials, we're going to be extrapolating out here, and then the uncertainty in our model is going to grow dramatically and just be no good. Over here on the right, we have our database for weldability. There's about 1,000 alloys in it, in which case we've got loads of data. We've got lots of data, we could build up a very precise model of the variation of weldability with composition. And what we want to persuade our machine learning tool to do is to first go and plot internally the graph of weldability versus processability. You see I put on it the blue and orange points. We want to see the direct link between those two, that it's just a straight line, correctly scaled. And because it's a straight line, it's going to be very easy to learn from just the 10 data points that we have available. And then, once it's established that link, it will be able to use the model it would develop over here on the right for weldability with composition to first work out, for a fresh composition, to work out the weldability, and then use this simple one-to-one relationship in here to then go and work out the processability, and then print out our final model of processability with weldability. Then we can see here we're going to get a much tighter model, much smaller uncertainties, and over here on the right we will be able to print out or be able to extrapolate easily with smaller uncertainty. And we're able to do that because effectively we're interpolating in this space, and we're also interpolating in this space here. So that's the strategy and the mathematical framework that we would like to set up, and the way that we're going to do that is we're going to have to completely rejig our neural network model. As we see here, there's a big problem that if I want to work out the processability, I really want to use the weldability as an input, but I'm stuck because it's on the output side. And so this information can never inform ourselves about the ability for direct laser deposition. So what I'm going to do is change the topology of our network to look much more like this, where now the weldability is an input. It can be fed through the neural network to up here work out what the processability is. And all I've got to do is be very careful, firstly, to make sure that this neural network is orthogonal to the identity operator, so I can never take in a value for the processability and immediately spit it back out. I want to predict processability. And secondly, I'm going to have to be very careful because some of these inputs are sometimes going to be available and sometimes not. Sometimes for a given composition I will have access to the weldability information, and when it's there I should exploit it. And sometimes I will not have that information available, and so the neural network should first take in composition, spit out weldability, then feed that information back in, and in the second pass, take in the weldability to predict the processability. So we set this up mathematically with this recursive setup. I can show you basically how it works here. We've got our three pieces of input information, and if on a first cycle I only have composition available, then I've shown it in colour, whereas the weldability and processability information is missing, and so I've shown them in grayscale. Now, because our neural network is a mathematical formula, it's going to need some inputs. We're going to need to put these values in, and so we could guess what those are. And the first good guess for what the weldability is, if I don't know, could just be the average of all of the other weldabilities that I do have access to. So I can just put in an average there. Then with this first good guess, I'm able to pass that through my first neural network, and here it can take in the compositional information and pass it down to the weldability. The processability is still going to be a complete guess, and the composition, it's always knows. And if I always knew it, what I really should be doing is just passing that value straight across. And actually, physically, what we do for working at this one is we actually take a mixture of maybe half of the prediction for the weldability, half of the old value, and then on a second cycle, maybe we could refine our prediction. Then we can go through a recursive setup several times. Now that we have the weldability, it can pass down and predict for us what the processability is. And so one can set up a neural network just like this. It's got several layers in which you recursively go through and refine your suggestions until you're able to get good predictions for all of those output values, and then we're truly able to use the information of the weldability to help infer for us what that very difficult to predict processability is. And so with that, that's the basic form of our neural network, able to handle missing input values and exploit property correlations. So with that now set up, we can go off and actually start to design some of these engines. And to do that, we're going to have to think about what do we want from the material back here. It's no good just designing something that will be good, have good processability, because we might be forgetting to go and optimize the melting point, and we might find it just falls apart. Or we also got to think we need to find a material that's going to be commercially viable to actually be able to sell it one day. And so you have to go off, talk to the engineers, and got off a list of all of the physical targets that we need to get right for this engine. So I've got right at the top here, very important, it's got cost. It's got to cost less than $25 per kilogram. Down here is the processability of the alloy within direct laser deposition. In actual fact, that is measured by an aerial density of cracks and defects that are formed in the material as it's undergoing several thermal cycles, and we need that to be less than 0.15% per unit area. What else have we got? Where's the oxidation resistance we're going to look at later. We need to remember that the engine, the components in very hot conditions with air rushing past and the surface can effectively burn and get damaged, so we need to avoid that. So we've got here a slew of all of the physical properties we've got to get right, and so to predict these we've got to go off and get models for all of them. Typically that would be from an experimental database. For some of them, like, I've got it here, yeah, that's a phase behaviour, the mantic gamma prime in the sample, it's up here, the mantic gamma prime in the sample, it's a particular phase that's formed. We know physically what we expect. That's something that we actually get using the CalFAT method. It's a thermodynamics tool. As we can bundle together all of these sources of information, we get very different amounts of information per quantity. There's also some other hidden ones, like the weldability, that we're not setting targets on. And we can go off and train our machine learning tools to predict all of those, go off, propose the material that we think has got the highest likelihood, the highest probability of exceeding all of those targets simultaneously, to the one most likely to work in the only experiments that we're allowed to perform to do, because they're very expensive to perform. And this is the material that we proposed. You see here, I've shown here the elemental makeup of it. It's got 10 different elements in. The balance here is nickel. It's basically nickel alloy with some other additives. It's a very complicated alloy. And we're able to design something with more elements in than the usual number that could be found by an experimental process of trial and improvement, because we're designing it on a computer, we can scan through these elements very quickly. And because we're able to make a more complicated alloy, explore new elemental space, that gives us the opportunity to design a better alloy in a new space than has previously been accessible. So at least there we've got a good chance to find something better. Now we also need to tell the direct laser deposition team how to make the alloy. It's really 10 variables. I've just shown 2 of them here. We've got this exposure parameter, which tells you basically how quickly you do the process. And we've also got here a heat treatment that we apply after the material has been manufactured in order to get some of the phase behaviour correct. And so we're able to design the whole material. That's where my work in this ends, and then we can pass the composition across to our experimental colleagues. In this case, it was partly done in the Rolls-Royce University Technology Centre in Cambridge in a group of Howard Stone, where they started preliminary studies of this material, and then once we were confident in some aspects of it, it was passed over to a direct laser deposition company in the UK called Material Solutions, who could actually go off, really print it for us, and start to really test its properties. So I shall show you some of those results, and the first thing that we do is we make a sample of it and look at it under a microscope, and that is what you see. It's a two-phase material. It's got that light grey precipitate in it. It's basically a nickel solid solution with a couple of other elements in. And within that are formed these dark-coloured, dark grey precipitates. That's at the phase called gamma prime. And they are there to give the alloy its strength. And it works a little bit like concrete. As dislocations move through the sample, cracks in concrete, they would get pinned by those precipitates that are formed, and they really give the material its strength. So here it's vital that we get the crack phase being formed, that we avoid about 60 other phases that could be formed in this material that we do not want, and that those precipitates are of the correct size and do not evolve with time to tell us that we've got the heat treatment process correct. Then once we've done that, we need to look at this again with a microscope and to go and look at whether any cracks and defects have been formed due to the thermal cycles that it has been pushed through. Now it looks good from this image, but there are actually some defects there, and we can go off and count those. And I've got a graph of those here with the amount of, or percentage of aerial defects formed on the y-axis versus on the x-axis one of the parameters that controls the direct laser deposition process, this exposure parameter. Now we propose this exposure parameter here of 0.9, but because we recognise that it was really difficult to design this alloy, and we're taking big leaps of faith when we're doing that link to weldability and other things, that we really needed to test this, and so we paid for additional experiments to be performed to plot the amount of defects as a function of this crucial exposure parameter.
Is it oxidation or what?
Sorry?
Is it oxidation or is exposure parameter?
The exposure parameter is how slowly do you do the 3D printing process.
Is it oxidation or?
Sorry?
Oxidation.
So that's one problem that can occur, but usually it's the amount of, sort of heat that you're pumping into the sample and how much you're heating this layer below. And that causes real problems, these additional thermal cycles. So the big problem here is going to be cracks. Now there's going to be in 2 slides' time something about oxidation. That's tested in a different way. Yeah, and for the amount of defects being formed, we don't want the defects, we want to be below 0.15, so in the grey shaded region of the curve. And we can see that if we'd have chosen this exposure parameter up here, then the alloy wouldn't have worked. But our choice of 0.9 in the safe region, where it looks like here, we're able to make good predictions, and we're well within the allowed number of defects. So that's one physical, yeah?
Can this parameter go above 100?
It can do, yes. But then other problems occur with the alloys. There's a real balance you have to get made, and I think if you change the exposure parameter, if you make it too small or too big, the size of those precipitates changes, and so you don't get the strength properties out of the alloys. It's a real multi-dimensional mess that we have to be able to navigate in this system. And it's even doubly more complicated because as you're using the alloy in the engine, it's operating about 900 Celsius. And so the size of the precipitates change. You've got to get it right at the beginning of this life cycle and also correct at the end of the life cycle. Right, so that was the amount of defects. Another property that was very important for us to get right is the yield stress of the alloy, which here again we plotted as a function of another of the processing conditions, because it was difficult to predict. That's the temperature, the heat treatment you apply after you've made the material. Now here we want the yield stress to be above 200 megapascals, so just on the graph, at a temperature of 900 Celsius, that's this bottom set of points, but we've got another set of measurements up here at 780 Celsius. And we see that actually all of the alloys, all of the choice of heat treatment temperature here would have been fine, provided we don't go above this temperature, which is where it melts. Well, we were proposing to design a material within this grey region, and it looks like the yield stress here is well within the proposed limits, so that looks like it worked well. And then the final parameter or property that I can show you that we measured is the oxidation resistance. So unlike you mentioned, I'm going to show you the oxidation resistance that it would accumulate during service of the material. So in which case, to measure that, you take a sample of the material, you put it on a very delicate pair of scales in a furnace at 900 Celsius, and you measure how the mass of the material increases with time as oxygen atoms start to stick onto its surface. And we've got that graph here. Here's the mass gain as a function of the time. Up here we've got an alloy that was previously being considered for direct laser deposition, and here's one of the big problems with it, is its oxidation resistance is not very good. You can see the mass gain shoot up there, whereas our target is this grey region that's below about here in the graph. Now we've got here in the dark magenta, no it's not, sorry, the light magenta area here is our prediction of the mass gain of our system. It's got a bit of uncertainty on it because we're not quite sure. We could do reasonable predictions of this, and you can see that it's only just about good enough. And that's because we had to allow so much leeway on that processability parameter, because it was so difficult for us to predict at very large uncertainties that we were really pushing the boundaries in almost all the other physical properties. So it's only just about predicted to work. But luckily, in this case, our actual experimental measurement, which is this darker purple line, have actually worked a little bit better than we expected, that they are within the expected threshold, and so this alloy did satisfy the oxidation requirements. So that was a real big win for us. This is a very important property for them. We're very pleased that it has worked out well, and that's just some of the properties that we measured. There's a few more that I can show you after the talk, if you are interested in it. And that's gone really well. They're now actually printing some components for an engine out of our material. That's what one of these combustors actually looks like, and it's now undergoing some further testing. And so that's how we've been able, in this case, to be able to combine together different experimental measurements together with a little bit of computational work in order to design a new alloy. And you saw how important it is that we can link together different experimental quantities to use probability to help guide the extrapolation at very difficult to measure processability. However, our method is completely generic, and we can apply it to design many other types of materials. And another one that we've been doing is almost at the other end of the temperature spectrum. It's a project we've been doing entirely in-house in the physics lab in Cambridge, and that is to design a material for use as a cryogenic temperature thermometer. So there's one of these fridges, and this is what one of these thermometers looks like. This thermometer, you measure the temperature by measuring the electrical resistance of the material, and then you have a graph to convert that into temperature. Now the problem with these thermometer materials is that the behaviour of electrical resistance with temperature is not 100% repeatable from thermometer to thermometer. It's quite a complicated shaped curve over the full range of temperatures that you could be interested in. And that means that when you bought a thermometer, that somebody's had to go away, sit in a lab with a calibration thermometer, spend a lot of time plotting for you the curve of resistance with temperature. And about 90% of the cost of these thermometers is in that calibration. And so we were wondering, perhaps we might be able to use machine learning to propose a new thermometer material that has a simpler electrical resistance with temperature behaviour, and so it's going to be cheaper to calibrate. With that being the goal, we need to remember that if we actually want to make this have high impact and be useful, then we don't just want to get a simple relationship. There's other things our thermometer must satisfy. The next one down on the list here in the middle is the sensitivity of the thermometer, which is measured as the ratio of temperature to resistance and its derivative. And this encapsulates that we want to be able to measure temperature similarly accurately at both low temperatures and also at high temperatures, be a really useful, practical thermometer. And the other one down at the bottom is very important, that some of these thermometer materials actually evolve with time and evolve as you push it through thermal cycles. And that makes it very difficult to use. What we want to do is try to design a thermometer that's going to be stable as a function of both the number of thermal cycles you've pushed it through, and also make it stable as a function of time. So you can leave it in your office drawer for a year, take it back out, and it will still work and not evolve at room temperature. So to do this, we actually were relying on it's almost a slightly new quantum mechanical trick that's not been applied to thermometry before. It's something analogous to the Conduit effect of atoms hopping back and forth in a lattice. But in order to do that, we had to combine together many pieces of knowledge. That to get the computational trick, or the quantum mechanical trick to work, we had to perform some density functional theory calculations to understand the energetic landscape that our atoms were sitting in, and we also had to put in, we had about 100 pieces of information for that. We had to put in this sort of analytical knowledge that we had of the landscape, which was, because it's an analytical formula, we can make a huge database of results. So what's there, 100,000 of them. And we also had to understand the thermodynamics of the materials, so we had, a few thousand CalFAD thermodynamic simulations to help us. And then we also had a little bit of experimental information from older papers on this thermometer, and also a couple of experiments we performed in-house. And so we're really relying on our ability to merge together all of these very different sized data sets to get, for example, our analytical knowledge, which is a huge database, and guide the extrapolation of that rare experimental data. Now, to do this, we also, of course, are taking a lot of time to do these DFT and experiments, and we want to work out what are the most useful simulations to perform. And to do that, we could run our machine learning in another way, a method called reinforcement learning. So that's one that, rather than the standard approach, we build up a big database of simulations. Here it's the thermodynamic ones. Build up a database and train our machine learning. We can instead do a small number of simulations that make a small database, make our machine learning model, and then scan through the machine learning model to explore materials that are a combination of interesting looking, and we are extrapolating, so there's a large uncertainty on them, and therefore be really useful to perform some more simulations. So we put in this additional loop here, this reinforcement learning loop, to then request some new simulations that we put into the database to improve our model. And when you do this, you can dramatically reduce the number of simulations that you have to perform in order to understand the space. So we can do that, build up our model, go off, propose a material, make it, and this is what it looks like. It's a kind of gold germanium mixture that's undergone a very rapid quench, in which case it looks like a complete mess. The light white areas are gold, quite a bit of germanium in the dark grey are germanium with a small percentage of gold in solid solution. But that exact mess is exactly what we want, because in order to get it to work over, the effects work over a broad range of temperature, we know that the atoms be in a broad range of environments, which we can induce by putting them under this very rapid quench. So that's what it looks like, and we can then go off, or my colleagues can go and measure the electrical resistance, resistivity, as a function of now log temperature. And you see how we've made the material where this relationship is entirely linear between about 0.2 Kelvin and around 200 Kelvin. So it's entirely log linear over 3 orders of magnitude in temperature, which makes that a very broad range. It's much broader than the next best thermometer, which is linear over about an order of magnitude. And so here this is going to be particularly well suited to measuring these temperatures over a very broad range and be much cheaper than the expensive thermometers that need a lot of calibration work. And furthermore, some additional measurements show us that the material is stable over 25 so far cycles. That's where some poor PhDs you can put it in, take it out, and measure it over a period of 6 months to make sure it's stable. And now we've got a commercial relationship with a local cryogenics company in order to go off and sell this on the open market. So been very pleased with that work. So that's just a couple of the materials projects we've done. We've got some other alloys we designed with Rolls-Royce that were before the 3D printing one. We've been doing batteries for Samsung. I've very recently just done this project with a welding company to design some new steels for welding. Just saw the results of that last week. Working on a materials database company. I've got a PhD student at the moment, sponsored by BP, to design some new lubricants to merge their classical molecular dynamics simulations together with experimental data. But then in the completely mercenary step, we noticed that the maths would work just as well on drug design, for small molecule drug design, as it would do for doing things like small lubricant molecules. But notice that drug companies have far bigger budgets than materials companies. And so there's a very strong temptation to go off and apply it to drug design, which I'm now I'll show you in the last 10-15 minutes or so, had a lot of very fun and success in. So when working in drug design, we've been focusing on just actually one part of the drug design process, and that is the first step, in which we consider putting a drug into a person. I hope that's adrenaline, and then that changes the behaviour of certain proteins in the human body, and then that has an effect on the human body, which here makes you run quicker. Now there's two big pieces of understanding we're going to need here. Firstly, there's about 10 million drug chemicals you can just buy off the shelf, and that can influence any or all of 10,000 proteins. There's a big matrix here we need to fill in, and then once we've worked out what the proteins influence are, then you've got to work out what actual effects they have on the human body, and that's a completely different problem. Now we have not been touching this one at all, we've only been working on this side of the problem. Now this is really going to be almost the ultimate sparse data problem. Said there's actually 10,000 proteins and about 10 billion drugs you can just buy off the shelf for testing with. And that data set, that matrix of activities, is only about 0.05% complete at the moment. It's a hugely sparse problem. Now here, we've been testing ourselves on a subset of that data that was put forward by another drug company called Novartis as almost a benchmark for drug design, in which case they've got this 159 different proteins and 10,000 compounds. It is a much more dense data set, but that one is 5% complete. And the challenge is, can we train off some of this data, train our neural network off it, and then start to fill in the gaps? And in which case, in order to test whether you could fill in the gaps, they had a separate training set and validation set of data, that this one was top secret and remained hidden. And furthermore, to make it particularly difficult, they set it up that to represent a real-life drug study where the training data came from one region of chemical space, whereas the validation data was for a different region of chemical space, a different sort of type of drugs, to replicate a real-life drug study where you've got some data from some other people and you're trying to explore a completely new family of drugs. As this is necessarily going to involve a lot of extrapolation, much like how we were linking 3D printability to weldability. Now, there's a little bit more information that we have, and that is that we know the chemical structure of all of the different drugs. We've got up here, you can come up with many different chemical descriptors. Up there, I've counted the number of oxygen atoms, nitrogens, number of benzene rings, as local variable descriptors. We've also got the total molecular weight as an entire molecule descriptor. But actually, you can come up with hundreds and hundreds of these chemical descriptors. It's a complete data set, a bit like how we had composition, and I've shown that here in red, where of course this top 3/4 of the data set is in one region of chemical space, and down the bottom here is a separate region of chemical space. Now, the typical way of doing machine learning would be to take as inputs these chemical descriptors and your outputs to be one column of proteins, and then for where you do have protein data, you can learn the link in between them, train the model, and then apply it down the bottom. But the correlations between chemical descriptors and protein activities is rather weak at best, and you don't have that many data points to learn of, and so it will turn out it doesn't work very well. But what we notice is there's additional information here that many of these proteins are quite similar to each other, and there's some pretty strong protein-to-protein correlations in this data set. And so what we actually want to do is learn the protein-protein correlations, and where we do have protein activity data, use it to inform where we do not, where there's data missing. And this is necessarily going to require a tool that can take in missing input information. And sometimes we have those protein activities, sometimes we don't. And then we really need to exploit them, and we're not. We need to not, our maths mustn't fall over, and it's got to find another way. So we went off, we trained our machine learning for exactly the same one as we used for materials on this system, and then we can start to make some predictions on that validation set. Now, here to measure the quality predictions, we use something called the coefficient of determination, a big R squared. And if you get 1, it means you're making perfect predictions on that validation data. 0 means that you're doing the most naive prediction possible, which is just to predict out the mean of the numbers. And if you're negative, it means that it's absolutely rubbish. And this technique here, random forest, is quite a common one that's been used on this problem before. And you'll see it's not performing very well because they're having to extrapolate in chemical space, and the average of the training data is not the same as the mean of the validation data, so it's just not worked at all. Now, the next method here, something called PQSAR, which is like an enhanced version of the random forest, except they're putting in the some additional sort of physical chemical information that they know about using their innate knowledge of chemistry, and that does better. So that was the method of the people that proposed this data set up this challenge, and that gets an R squared of about 0.19. Now, the next people to come along, who are not publishing this, I've only been told by the authors of that paper, is Google had to go with their method and it didn't work very well. And then we had to go with our neural networks, and you see it does a little bit better than the PQSAR, so we're really exploiting those protein-protein correlations. And although it's better than them, it's still not very good. But really, that R squared of 0.21, 0.22 or so is not good enough for practical drug design to be able to replace experiments. We really need R squared all the way up above about 0.7. But at this point, we've got one additional trick up our sleeves, which is unlike those other methods, we understand the uncertainty in our predictions, and we're going to be able to really exploit those. We've got here a graph actually of just 4 of those proteins and their predicted activities, and our method not only prints out the expected activity, but also the uncertainty in it. And maybe for some we're extrapolating further in chemical space than others, more training data for some than others, and so the uncertainties can vary quite a lot. Now, if I plot on top of these the validation data that we are blind to, then if we've done a good job of those uncertainties, then usually the validation data will hopefully be within 1 standard deviation of our predicted values. And then we need to remember that when we are measuring that R squared metrics for how well we're doing, we're calculating something like the sum of the squares for those grey arrows. And we can immediately see a big clue here that we can exploit, that on systems with bigger uncertainties, there's a good chance these grey arrows are big, and on systems with small uncertainties, those grey arrows are small. And so we might be able to play a little trick here, that if I just go and throw away the data that we believe is the 25% worst data, just leave the best 75%, then it will hopefully be the case those grey arrows are on average shorter and will do a better job of it. Or perhaps I could throw the next quartile away and just predict 50%, or just predict 25%. And now, our predictions will hopefully be much better, a much larger value of R squared. And so we can actually try that. I've got here a graph of R squared versus the amount of data we're filling in. On the right is the 4 methods I showed you earlier, where we're filling in all the data, but we can go on and plot this curve, where by throwing away the data, we're able to dramatically boost the R squared upward, all the way up to beyond 0.9, which is going to be easily good enough to actually really be able to replace experimental measurements. Where I think you need above about 0.7 or so in drug design, so we can predict a few percent of the data with sufficient accuracy to actually be able to replace experiments. So although this might appear to be a little bit of a cheat, and it kind of is, in some ways it isn't, because we also need to remember that in real life drug situations and also in material design, that we're trying to find a new drug or new material to satisfy a set of targets. We're not trying to, for a particular composition, predict what the properties are. We only need to find one composition that will satisfy the targets, and there's probably a lot of materials out there that would work. And there's a lot of drugs out there that could cure a particular ailment, and we only need to find one of them. Provided it's in the few percent that we can predict readily, then we're in good shape. And if you just think about cures for things like headaches, there's on the market, there's all these common ones you can just buy from the pharmacy, and many more that are prescription. They all work by entirely different mechanisms, but they all cure the same ailment. And in drug design, you only need to find one of those few solutions. And so it doesn't matter that we can't predict all of the possible drugs and proteins, we only need to predict a few of them. And that's where just being able to selectively focus on the data which you can make really good quality predictions for is going to be very important. So we've had a lot of fun doing this drug design. We've now got a commercial agreement with a software reseller called Optibrium to take that to market and go through their marketing channels. We sell it around the world, and we're currently working with them to embed it in the next generation of software tool that should be released in October 2020. So we're very excited about that. So in summary, I've shown you today how we develop this unique form of machine learning that can really train of missing data. It's able to take together very expensive and valuable experimental measurements, merge it with some cheaper experiments, and merge it with computer simulations, and use those easier to perform measurements to help guide the extrapolation of the expensive values. Now, by doing that, I've shown you today how we first used that to design these new metal alloys for use in direct laser deposition that have been experimentally verified and are now undergoing some real-life conformance testing. I showed you the thermometer, and also showed you the work that we have done applying the same maths but to small molecule drug design. So, following this success, we've actually, as was mentioned at the beginning, also formed a startup company, Intelligens, which is now really driving forward the commercialisation of this, both in drug and materials design, and also looking at a couple of other verticals. So with that, I'd like to thank you again for your attention, and I'd be happy to take your questions.
Regarding the nickel alloy, did you do all the tests that didn't correspond to the prediction, or did you try some other material before it didn't correspond to the prediction, or first guess, successful?
So in this case, we realised this was particularly difficult, which is why we did the other experiments. There are a couple of properties that are very marginal, and our observation is very close. We always knew it was going to be close. But we typically designing these results at the moment with about a 90% chance of satisfying all the properties. Because we're actually playing quite safe on them. And we usually have to do that because the experimentalist will only allow us to do one. But that set of experiments is several $100,000. And so I only get one chance at it. Now we've had another point in which we were tasked with designing a new alloy to that. Where just from the theory predictions we could say there's about a 90% chance that there is no material out there in this planet that will ever work. And with that information then we have to shut down that line of investigation, and then you task them to do some others. There's a disappointing negative result, but it was very important.
I have a question also regarding the nickel design. Could you invert your neural network? Except these are the predictions, and so You don't do it. You start with some composition and then see if it fits. Don't you invert that?
It is possible to invert, so as we have that neural network where everything is an input and everything is an output, you can put properties in as an input, and it will go up and spit out composition as an output. So it's mathematically possible, but it's just not very computationally efficient to do it that way. You have to train a rather much larger neural network than we really have time to do in order to do that process, and we find it better, more efficient to go from composition to properties and then scan through millions and billions of compositions.
If you said 25% gamma prime,
yeah,
this is an error which is for sheets of rolling, and so evidently this error will be very good for welding also. The welding problems come down with 50, 60, 70% in volume for gamma prime.
Yeah.
So what is new there? Because this is an error which will anyway work for welding, no problem. We know that. But what is new with your approach? I don't see that.
Well, we've got to be able to find the right compromise between all of those material properties. If you just want to find something welding, you can find it. If you want to find something good at 3D printing which is similar to welding, you can just print it out. But there's always other problems like that. C263 had terrible or not good enough oxidation resistance. So what you can do what we're doing is interpolating between lots of different properties, getting the compromise right between all of them. That we wouldn't be able to go off and find the highest melting point temperature, melting point material ever, because we'd be dramatically extrapolating and then it won't work very well. It must always be interpolation.
But what is new with this error?
Well, so it's the material composition, just new. It's got different elements in it, more complicated composition than before.
This is a normal superalloy.
It is a normal super. It's not a completely new family of materials, unlike that thermometer. It's a standard superalloy where we've got the right mixture between properties for that purpose. Some of those other materials we made before was also superalloys that were tuned for other properties in other places in the engine. It's just getting that compromise right is a very expensive problem.
So for the problem of the error design, I noticed that you have a very precise composition. So is there any handle on the uncertainty or the sensitivity that say if I slightly alter the composition, how would that alter the property?
Yes. Yes, we certainly have to be able to do this because when we go off and patent these alloys, we really want to patent a range of compositions. And so when we're going off and predicting that, we encourage the tool to explore each element separately around our central composition to find what the minimum and maximum bounds are. And then, of course, from Rolls-Royce and the university's point of view, we need to be able to justify as large a region of composition space as is possible. And so we have the way to do that, you just push it in each direction separately.
I have two related questions. Right next to that combustor and that turbine, there are these highly engineered blades that have a microstructure which is engineered to have very low creep.
Yeah.
And so that suggests that putting a microstructure into the neural net as a training set could be important, but that's an entirely different kind of data. So I'm guessing you've thought about how to put microstructure into the systems.
Yes.
Okay.
Yeah, so our first project with Rolls-Royce before that one was to design the discs, that kind of size, the blade to attach to. And it turns out for their engines, the discs are the critical component rather than the blades. And then, yes, then we have both the microstructures I showed you from Calvert, and we have other tools using something called Pacifical to work out the evolution of that microstructure as a function of time, in order to be able to understand the evolution over the lifetime of the engine.
That sounds much harder.
Yes.
So the related question is, for the combustor itself, it may turn out that the optimal solution would be the alloy that you have, but covered with a ceramic thermal barrier coating, which is kind of absolutely a new choice that the neural net doesn't know how to make such a prediction. And so we're kind of stuck thinking about the old engineering ways of doing things.
No, you're absolutely right. This is, I was also mentioned with the gentleman here, that we're really interpolating in space, and it can't make these big intellectual leaps, so it needs to be much cleverer than it is in order to do that. And there are separate research efforts into coatings. We could go and design coatings in a separate investigation if that was viable. Yeah.
Finding new drugs, as you know, is very expensive. Now, you had 4 drugs up there against pain. You had 4 drugs, penicillin, whatever, against pain. So why don't you take a completely different philosophy? All these drugs have been developed. We don't want any new drugs. We want new combinations of drugs.
Yeah.
We should find synergies using your method. You're there. Much cheaper.
Yes, so this repurposing of drugs is actually what one of these companies here, where they've gone. Oh, there they are. That e-therapeutics company that we're working with, that is exactly their business strategy. That they've got this clever network technique that's developed at the University of Oxford. We're working out exactly how to do this. And the only thing they were missing with this knowledge of drug to protein database, and that's what we've been providing for them.
You believe things from Oxford? You believe things from Oxford?
Well, as long as they pay us. And they also came from the University of Newcastle, which is a much more trustworthy source.
Some of these alphas, sorry.
Hold on,
Okay. I was just wondering how you measure quantitatively processability.
So that was the percentage of defects that are formed.
But what kind of defects?
So in this case, they are little pores that are formed when you go through the thermal cycles. There's also a little bit of cracking.
Because then if you start seeing cracking, I guess this kind of removes the possibility of using it. So you have actually somehow to distinguish between the kind of defects in the way you quantify processability.
Yes, that could be done. That's beyond the study that we were doing for them.
Because in the example that you showed in the end, I didn't see any single crack. So somehow we were in the best zone in terms of defect contents. And then I was just wondering if it's just borrowing the most weldable alloys, and then really looking in this region and optimizing there, or if you really were away from the most weldable alloys.
No, the tool would tend towards the highly weldable alloys that also satisfy these other properties, which are quite a lot of targets that you had to get right.
So you had some kind of weights on the weldability.
Yeah, which is done by, well, all the properties are weighted as probabilities. So for each one, we make a prediction, then we look at one standard deviation below it to compare that to the target, and we're working out a probability of each target being satisfied, and merge all this together to get an overall probability of the alloy working. And when I said earlier that we were pushing the oxidation resistance really to the extreme, it's because we can make good predictions for it. And so we're only just within the expected uncertainty, whereas for this processability, that is really difficult to predict. There were quite large uncertainties in our predictions. So we had to, the expected value was well within the target, but there's a decent chance of it would work.
We'll take 2 more questions from Duncan and run after.
So thanks. So the alphas are somehow quite empirical. Once you've developed a successful neural network, can you then also interrogate it to improve the mechanistic understanding? What's going on microstructurally in the processing, etc.?
There is a little bit of that goes on, that we could go through and look at the weights inside the neural network and imagine in your mind it's a Taylor expansion and can pull out a couple of already known physical laws. But it's quite hard work, and we haven't been able to discover any new physical laws from it.
Well, I wouldn't put it this way exactly, coming from an image processing background. When you're debugging this network that we don't know if it's a recurrent, convolutional, I mean, for us it's just a black box here in this presentation, have you managed to extract some sort of, I'm not talking about physical laws, just some, let's say, design guidelines that might be useful to engineers in their daily work for example, so you can add them in a textbook that, you know, given this debugging of this thing, we found that this could be nice. So, you know, a new teaching method for smaller components and stuff like that.
Yes, there is. We have done a little bit of that, particularly on the more recent BP project. You know, able to understand that PhD students, they've been very enthusiastic on understanding that when you move a branch for hydrocarbon like this and that, and this temperature goes up by about 2 degrees Celsius, which could be useful guidelines that build up physical rules of thumb for textbooks, etc.
Okay, and last thing, do you think that this method could work well for alloys that change composition over their volume? Because this looks like a static alloy. What about an alloy that starts with this percentage of carbon and then gets like a little bit different here and there to fit design particularities?
Yes, the method I set up and we've been using at the moment, we do that locally, but there will be some other practical considerations that one has to consider. Can you actually go and make this thing? Is there going to be some meat boundary in the manufacturing? And you could go and put those in. You would have to go and put those in as additional expectation values.
And one last thing, how about intellectual property? I mean, if someone else from another country, let's say a huge country like Russia, China, India, comes and says, wait a minute, we had already a neural network and we found this way before you. How can you deal with this? Because I see that you're speaking about commercialization, about off-the-shelf products, but you don't know secretly other military services what might have been developing.
So in those cases, well, we're in trouble if they patented it, but we can go into our code and block out regions space that we already know are patented, but if they haven't, it's that we can go off and exploit it ourselves. We may not be able to patent it, depending on how much they divulge the information, but we can still go off and exploit it ourselves.